Now we are going to discuss elements of traffic analysis. The primary function of a highway is to provide a transportation service. In an engineering context, this service is measured in terms of the highway's ability to accommodate vehicle traffic safely and with some acceptable level of performance. That is, providing acceptable vehicle speeds. The analysis of vehicle traffic provides the basis for measuring the operating performance of highways. In undertaking such an analysis, the various dimensions of traffic, such as number of vehicles per unit time, that is the traffic volume, vehicle types, vehicle speeds, and the variation in traffic volumes over time, must be addressed because they will influence highway design. The selection of the number of lanes, pavement types, and geometric design. And highway operations, selection of traffic control devices including signs, markings, and traffic signals, both of which impact the performance of the highway in terms of its ability to handle vehicle traffic. Now we are going to discuss a few important terms: traffic flow, speed, and density. Traffic flow, speed, and density are variables that form the underpinning of traffic analysis. First, look at the traffic flow. The traffic flow, this is generally denoted by small q, is a measure of volume of traffic on a highway. Flow is defined as the number of vehicles n passing some given point on the highway in a given time interval t. So this is the formula for the traffic flow. Q is equal to n over t. So here you can see that Q means traffic flow, N means number of vehicles passing some designated point on the highway, and T is the time interval. In general terms, Q is expressed in vehicles per unit time. Now look at the term density. Density is sometimes referred to as concentration and is defined as the number of vehicles traveling over a unit length of highway at an instant in time. The unit length is usually 1 mile, thereby making vehicles per mile the units of density. So K, that is the density or the concentration, that is equal to N over L. And you can see that K means traffic density, N means number of vehicles, and L means known length of highway. Now look at speed. Speed, here we are using small u, the symbols for the speed. Speed is the rate of change of distance with respect to time and is usually measured in either miles per hour or kilometers per hour or feet per second or meter per second, depending on the application. The speed of a vehicle at any time t is the slope of the time-space diagram for the vehicle at time t. In the figure on the next slide, vehicles 1 and 2 are moving at a constant speed because the slopes of the associated graphs are constant. So look at this diagram. This is time-space diagram. So here the word space is being used for the distance. So distance, and this is the time. So where you are having the constant slope, it means the speed is constant or uniform. Well, if you just look at the previous slide, that is the figure, vehicle 3 moves at a constant speed between time 0 and time t3, then stops for the period t3 to t3 double dash. The slope of graph equals 0, and then accelerates and eventually moves at a constant speed. So you could be able to understand this thing when you will be looking at the figure. There are two types of mean speeds: time mean speed and space mean speed. So two types or two versions, you can say: time mean speed and space mean speed. So first look at the arithmetic mean or time mean speed. It is the arithmetic mean of the speeds of vehicles passing a point on a highway during an interval of time. The time mean speed is determined by this formula. So this is the arithmetic mean or time mean speed, and we are having just the summation of the speeds of the different vehicles and dividing it by the total number of vehicles. So here u sub t bar, that is the time mean speed, u sub I individual speed measurement, and n mean the sample size, that means number of vehicles. So just look at this time mean speed. Let's say there are three vehicles which are moving with the speed u1, u2 and u3 respectively. So just add all these speeds of three vehicles and divide by the total number of vehicles, which are 3 in this example. So this will give you the time mean speed. Then look at the harmonic mean or space mean speed. It is the harmonic mean of the speeds of vehicles passing a point on a highway during an interval of time. It is obtained by dividing the total distance traveled by two or more vehicles on a section of highway by the total time required by these vehicles to travel that distance. This is the speed that is involved in flow density relationships. The space mean speed is found by using this formula or that. Basically, uh, both formulas are same. Both formulas are meant for u sub s bar. So look at that. Here n, l and the time, and here n and the individual speed of the vehicle are involved. So you can see that u sub s bar, that is the space mean speed, and the number of vehicles, t sub I the time it takes with the ith vehicle to travel across the section of highway, and u sub I the speed of the ith vehicle, and L is the length of section of highway. So just look at this example. Let's say there are three vehicles. So you can see the number of vehicles are in the numerator, and the denominator we are having 1 over u1 plus 1 over u2 plus 1 over u3, and U1, U2 and U3 are the speeds of the three vehicles. The time mean speed is always higher than the space mean speed, because the definition, if you just look at the definitions are different for these two speeds. The difference between these speeds tends to decrease as the absolute values of speed increase. It has been shown from field data that the relationship between time mean speed and space mean speed can be given as this. So look at this formula, and here this sigma is the new thing, that is sigma is standard deviation in miles per hour. A direct relationship developed by Garber and Sankar using data collected at several sites on freeways is shown below. So this relationship is also there. Figure also shows a plot of time mean speeds against space mean speeds using the same data. So look at this one, time mean speed versus space mean speed. So here we are having the time mean speed in kilometer per hour, and here the space mean speed in kilometer per hour. So you can see that the trend line is this one. So we are having the direct relationship between the time mean speed and the space mean speed. Next term is the time headway, small h. It is the difference between the time the front of a vehicle arrives at a point on the highway and the time the front of the next vehicle arrives at the same point. Time headway is usually expressed in seconds. Now look at the time-space diagram again. In this, I mean to say, if you just look at this example which is mentioned over here, for example, in the time-space diagram that I have already shown, the time headway between vehicles 3 and 4 at D1 is h sub 3-4. So look at this figure, concept of clearance, gap and spacing or headway. So you can see that front of this vehicle and the front of this vehicle. So this distance is the spacing, and obviously certain time is required for this vehicle to reach this point, and that would be the headway in seconds. So this is the gap, clearance, and the L is the length of this vehicle. So this is the time space diagram. So you can see here where the slope is constant, it means the speed is constant. Where this line is perfectly horizontal, it means the vehicle is not moving. Now look at the space headway D. It is the distance between the front of a vehicle and the front of the following vehicle, as I described earlier. It is usually expressed in feet. The space headway between vehicles 3 and 4 at time T5 is D3-4. Flow density relationships. The general equation relating flow density and space mean speed is given as flow is equal to density into space mean speed. So this is very useful relationship, that flow is equal to density multiplied by space mean speed, or you can say Q is equal to K multiplied by U sub S bar. And here you can see that Q is the average volume of flow, K average density or concentration in vehicles per hour, and U sub S bar the space mean speed, that is miles per hour or in kilometer per hour. Flow, density and space mean speed also depend on several other factors, including the characteristics of the roadway, the characteristics of the vehicle, the characteristics of the driver, and environmental factors such as weather. Fundamental diagram of traffic flow. The relationship between the density, that is in vehicles per mile, and the corresponding flow of traffic on a highway generally is referred to as the fundamental diagram of traffic flow. The following theory has been postulated with respect to the shape of the curve depicting this relationship. When the density on the highway is zero, the flow is also zero because there are no vehicles on the highway. You can visualize this thing very easily. As the density increases, the flow also increases. However, when the density reaches its maximum, generally referred to as the jam density, and it can be denoted by K sub j, the flow must be zero because vehicles will tend to line up end to end. It follows that as density increases from zero, the flow will also initially increase from zero to a maximum value. Further continuous increase in density will then result in continuous reduction of the flow, which will eventually be zero when the density is equal to the jam density. The shape of the curve therefore takes the form in figure A. Now look at the figure A. So you can see that along vertical axis the flow and along horizontal axis the density. So typical shape of the curve is like this. And you can see that here you have got the maximum flow corresponding to point E, and the density is K sub E. And at point B you can see that the density is K sub B, and then you can see that what is happening, that because of the congestion there is decrease in the flow as the density is increasing, and ultimately you have reached here where you have got the jam density. So corresponding to C point you are having K sub C, and here obviously the density is K sub J. Now if you just draw the tangent over here, the slope of this line will give you the mean free speed, and if you join this point B to this, so slope of this will give you uh, space mean speed at this point. So in this way you can see at point E, you can join this line to this point, you can join this point C to this point O. So slopes of these lines give space mean speeds for K sub B, K sub E and K sub C. Data have been collected that tend to confirm the argument postulated above, but there is some controversy regarding the exact shape of the curve. A similar argument can be postulated for the general relationship between the space mean speed and flow. When flow is very low, this point is important, when the flow is very low, there is little interaction between individual vehicles. Drivers are therefore free to travel at the maximum possible speed. The absolute maximum speed is obtained as the flow tends to zero. So you can visualize this thing. I will repeat that drivers are therefore free to travel at the maximum possible speed. The absolute maximum speed is obtained as the flow tends to zero, and it is known as mean free speed u sub f. The magnitude of the mean free speed depends on the physical characteristics of the highway. Continuous increase in flow will result in continuous decrease in speed. A point will reached, however, when further addition of vehicles will result in the reduction of the actual number of vehicles that pass a point on the highway, that is, reduction of flow. This results in congestion, and eventually both the speed and the flow become zero. Now we are going to look at the two figures, figure C and figure B. Figure C shows this general relationship, and figure B shows the direct relationship between speed and density. So look at these figures. So this one is the space mean speed versus density. So along vertical axis we are having the space mean speed, and you can see that when the density is zero you are having the maximum space mean speed, but as the density is increasing, what is happening? The space mean speed is going to reduce. And over here, as you are having the jam density, so you can see the space mean speed has become equal to zero. So it's quite easy to understand. Now look at this space mean speed versus volume. So you can see that this axis is again space mean speed, and this is the flow. So when flow is zero, obviously the maximum value of u sub f is there. As the flow is increasing, so what is happening to u, that is the mean space mean speed, it is reducing. So you can see that at this particular point onwards, as the congestion has started, so with you can see that ultimately now there will be decrease in the flow because of the congested flow, and ultimately it will reach here. That means the flow has become equal to zero. So that is just because of the congestion, or you can say the congested flow, that this point has reached. We have reached this point. Next term, hourly volume. Hourly volume is the actual traffic volume on a roadway in vehicles per hour, given the symbol V. Generally, the highest volume in a 24-hour period, that is the peak hour volume, is used for V in traffic analysis computations. Now look at this term, peak hour factor. The peak hour factor accounts for the non-uniformity of traffic flow over the peak hour, as shown in figure on the next slide. It is denoted by PHF and is defined as the ratio of hourly volume V to the maximum 15-minute rate of flow V15 expanded to an hourly volume. So look at the formula. This is V, that is the hourly volume V, and here this is V15, and it is being multiplied by 4, and in this way we are expanding this V15 to an hourly volume, because you know there are 60 minutes, so this is 15 V15 and it is being multiplied by 4. So again look at the definition. PHF, that is the peak hour factor, is defined as the ratio of the hourly volume V to the maximum 15-minute rate of flow expanded to an hourly volume. So look at this formula. This is the formula for PHF. And look at this one. Along the vertical axis, we are having the rate of traffic flow in vehicles per hour, and here the time, and we have considered 1 hour period over here, that is the peak hour. And during peak hour we are having this pattern of flow, and you can see that non-uniform flow is there over this peak hour. Okay, equation indicates that the further the PHF is from unity, the more peaked or non-uniform the traffic flow during the hour. For example, consider two roads, both of which have peak hour volume V of 2000 vehicles per hour. The first road has 1000 vehicles arriving in the highest 15-minute interval, and the second road has 600 vehicles arriving in the highest 15-minute interval. The first road has more non-uniform flow, and this is substantiated by the fact that the PHF of 0.5. And how you are getting 0.5? That is 2000 divided by 1000 divided by 4, and the answer is 0.5. So 0.5 is further from unity than the second road's PHF of 0.83, because in the second road we are having 2000 divided by 600 divided by 4, and that is 0.3. So this 0.5 is further from unity, so that's why here you are having more non-uniform flow. Now look at service flow. Service flow is the actual rate of flow for the peak 15-minute period expanded to an hourly volume and expressed in vehicles per hour. Service flow is denoted by SF and is defined as. So first look at this one. SF is just V15 multiplied by 4, and this thing can be written as V over PHF, because if you just recall the formula of the PHF, from that you can see that V15 into 4, it can be replaced by V over PHF. Returning to the previous peak hour factor example, note that the road with PHF equal to 0.5 has a service flow of 4000 vehicles per hour, and road with PHF is equal to 0.83 has a service flow of 2400 vehicles per hour. Now I need your special attention in determining level of service. Service flow will be used, not the peak hour volume. So I will repeat that in determining the level of service, service flow will be considered. Thus, the road with service flow of 4000 vehicles per hour will have a considerably worse level of service, even though both roads have the same hourly volume V. So obviously when you are having more service flow, so obviously the level of service will be low. So that's why you can see that the road with the service flow of 4000 vehicles per hour will have a considerably worse level of service, even though both roads have the same hourly volume V. Now the next term, the average daily traffic ADT. The general unit of measure for traffic is the average daily traffic ADT, defined as the total volume during a given time period in whole days greater than 1 day and less than 1 year divided by the number of days in that period. The ADT for a highway can be easily determined when continuous traffic counts are maintained. The ADT by itself is, however, not a practical measure of traffic because it does not adequately indicate the variation in the traffic in the year, the week, or different hours of the day. Naturally, we need an interval of time shorter than a day to more appropriately reflect the prevailing operating conditions. In most cases, a practical and adequate time period is 1 hour. Now, look at design hourly volume, DHV. The peak hour volume is the generally accepted criterion for use in geometric design. It is the traffic volume expected to use the facility and is called the design hourly volume, DHV. It is typically the 30th highest annual hourly volume. Now, what is the meaning of this 30th highest annual hourly volume? I have accommodated a few words over here and I need your attention. 30th highest annual hourly volume is the hourly volume which is exceeded by only 29 hours in a year, and all other hourly volume of the year will be less than this value. AADT is the roadway's average annual daily traffic. In practice, the K factor is used to convert average annual daily traffic AADT to the peak hour volume. K is defined as DHV over AADT. We have already discussed DHV. So DHV over AADT, that is equal to K, that is the K factor. Finally, in the design and analysis of some highway types, for example, freeways and multi-lane highways, the concern lies with directional traffic flows. Thus, a factor is needed to reflect the proportion of peak hour traffic volume traveling in the peak direction. This factor is denoted as D and is used to arrive at the directional design hour volume, that is DDHV, by the application of this formula. So DDHV, that is K into D into AADT. Now look at the operational speed. Speed is one of the most important factors in choosing a route or selecting a transportation mode. Economy, travel time, and convenience are directly related to speed. Highway speed is generally dependent on 6 conditions. And look at those conditions. The first one is that the capability of drivers using the highway. Number 2, the characteristics of the vehicle fleet using the highway. Number 3, the physical characteristics of the highway and its roadsides. Number 4, the weather. Number 5, the presence of other vehicles. Number 6, the speed limitations, both legal and because of control devices. The aggregate effect of these conditions determine the speed on that stretch of highway. The main objective in highway design is to satisfy the demands of the user in the safest and most economical manner. Provision should be made for a speed that satisfies nearly all drivers. Operating speed can be seen as the highest overall speed at which a driver can travel on a given highway under favorable weather conditions and under prevailing traffic conditions on a section-by-section basis. Now look at the design speed. Design speed is a selected speed used to determine the various geometric design features of the roadway. As per AASHTO, this is the definition of the design speed. Consistent with the desired degree of safety, mobility, and efficiency, as well as constrained by environmental quality, economics, aesthetic, and socio-political impacts, every effort should be made to use as high a design speed as practicable. An exception is made for local streets where speed controls are frequently included. The assumed design speed should be arrived carefully with respect to the functional classification of highway, topography, adjacent land use, and anticipated free flow speed. A few pointers to keep in mind. The design speed should be consistent with the speed an average driver is likely to expect. In addition, drivers adjust their speeds not according to the importance of the highway but rather based on the physical limitation and traffic thereon. A consistent design speed over a substantial length of roadway is an important factor. Any drastic speed changes should be avoided, and if such changes are necessary due to topographic constraints, should be gradual. Drivers should be warned well in advance of what to expect by means of speed zone signs and curb speed signs. AASHTO provides a thorough discussion of design speeds. In summary, the maximum limit for low or lower design speed is 45 miles per hour and the minimum limit for high speed design is 50 miles per hour. Now we have reached this topic, that is the running speed. It is necessary to know actual vehicle speeds occurring on a highway section. This is called the running speed and is equal to the distance traveled by a vehicle divided by the time the vehicle is in motion. When vehicle flow is reasonably continuous, the spot speed at a section is the equivalent average running speed. The average spot speed is the arithmetic mean of all traffic speeds at a specified location. On longer sections, several spot speeds measured along the stretch of highway may be averaged to give the average running speed. Now, the topic of free flow speed. Free flow speed (FFS) is the speed of traffic as density approaches zero. Practically, it is the speed at which drivers feel comfortable traveling under the physical, environmental, and traffic control conditions existing on an uncongested section of freeway or multi-lane highway. So here you can see these words again, that free flow speed is the speed of traffic as density approaches zero. So it is noted by FFS. Field determination of the free flow speed is accomplished by performing travel time studies during periods of low volume and represents a practical value in highway capacity analysis. Operating speed, as defined earlier, thus varies over a range of speeds depending upon the prevailing conditions when speed measurements are done. Figure on next slide shows the speed flow relationship for a typical uninterrupted flow segment on a multi-lane highway. The figure also indicates that the speed of traffic on a multi-lane highway is insensitive to traffic volume up to a flow rate of about 1400 passenger cars per hour per lane. PC per hour per lane, that means passenger car per hour per lane. So this point is very, very important, and you could be able to see this thing on that figure that is present on the next slide. I will repeat, the figure also indicates that the speed of traffic on a multi-lane highway is insensitive to the traffic volume up to a flow rate of about 1400 passengers cars per hour per lane. Now look at this one. This is the mean passenger car speed in miles per hour, and you can see that we are having the free flow speed of 60 miles per hour over here. Here the 55 miles per hour, 50 miles and 45 miles per hour. Why? Because you can see that the flow rate of about 1400, you are having these lines horizontal, and then you are having the shape of the curve like this. So here you can see that it is about up to 1400 that you can see when the lines are horizontal. Look at that. So in this way, uh, we have discussed some useful terms and concepts related to traffic analysis. Thank you.